we looked at flexure and bending stresses. So now we're going to consider bending shear. And as you recall from the beginning of this set of lectures, or this lecture 6 is what it's called, I used to try and cram all of this, the bending or the moment stuff and the shear stuff into one lecture, but I found that ultimately it's better to split it up, so that's why I think it's called lecture 6 twice. It's just all one set of notes. Right, so from this guy, right, our shear is defined as dm dx, and so that's what we're picking up here. And this is coming from shear, bending shear comes from change in moment, right? So if the moment changes along the length of the beam, then it generates bending shear. So then on the flip side, if the moment is constant along the length of the beam and doesn't vary, then the shear is 0. And as we know, moment is related to bending stress. All right, we went through this last time. Sigma is equal to negative m times y over I. And if we're typically in the YZ cross section, it would be moment of inertia about Z and the normal stress in X. So then it follows that shear stress is generated when the normal bending stress varies. So if we consider a rectangular cross-section, right, again, just considering a sliver along the length, dx, we have the width b, the total depth is 2c, and we're just considering, right, shear stress at a specific location within the cross-section. So if we want to know the shear stress at this height, y1, noted in the sketch, all right, so if we have the area shaded is shown, that is the area above that location where we're interested in the shear stress. So the shear stress times the width, b, times this length, right, the sliver dx, is equal to the integral over the area that we're calling A1, right, that area above Y1, of the change in normal stress, right? So this guy right here, because as you can see, right, considering both sides, equilibrium cancels out the sigma x, and we're just left with the change in sigma x. So this becomes negative integral over the area A1, substituting in our relationship for sigma x here, dm over Iz times y dA. So then we can write tau is equal to dm dx times the integral over area A1 of y dA divided by b and Iz. Or shear stress for dm dx times capital Q, which is that first moment of area, divided by B and Iz. So just write down here, capital Q is that first moment of area A1 about Z. And we'll go over the calculation for that in a moment. But that's essentially equal to A1 times Y bar, or we can call it Y1 bar, where Y1 bar would be the distance from the neutral axis to the centroid of that area A1, right? So we can define that as C plus Y1 over 2. And I know that's not immediately obvious, but I'll show you where that comes from as well in a moment, but we'll just finish this thought out. So Q is equal to B times C minus Y1. So that's the area A1, and then times C plus Y1 divided by 2. Let's see. So I'm just going to note down here, right, that's A1, and that's Y1 bar. So going back to that Y1 bar, the distance to this point would be Y1 plus C minus Y1 over 2, right? Coming from here, Y1 plus half of this distance here. And then simplifying that gets you C plus Y1 over 2. questions? Okay. All right, so continuing on, a few comments here. The bending stress, as we know, is going to be maximum magnitude at the extreme fibers, so top and bottom, right, farthest distance from the neutral axis. And at those extreme fibers, for shear stress considerations, right, if you're considering a point at the top, well, the area A1 is going to be 0 because there is no area above that point. And then if you're considering positions below the neutral axis, right, you would be, for example, this point, if you were calculating shear stress for that, you would consider the area below that point to the extreme fibers. So the closer you get to the extreme fibers, the smaller that area gets, and then once you're at the extreme fiber, A is equal to 0. So if A is equal to 0, it follows that Q is equal to 0, and then it follows that shear stress is equal to 0, right? So you know that the Q, or you can predict that that value Q will be maximum at the neutral axis, right, when Y1 is equal to 0. So that means that the shear stress will be maximum at the neutral axis as well. Now this is true for a rectangular cross-section like this, but if you have a shape where you have different widths along the depth, then it changes. So for a rectangular cross-section like this, your shear stress distribution would be parabolic following that pattern that you see. But I'm going to note here, right, so this conclusion is true for a rectangular cross-section, and then I'll make a note for general applications. All right, in general, the maximum shear stress is going to occur where Q divided by B is max within the cross-section depth, right? So we'll dive into that a little bit on the next page. Questions so far?
And this is just the shear stress due to bending, right?
Yeah, well, it's due to changing moment, right? So even if you don't have an applied moment, right? If you just have a point load, that will cause moment that varies along the beam, and that will generate a shear stress. But yeah, we call it shear stress due to bending, or bending shear, rather than maybe shear due to torsion or something like that.
Right.
Yeah.
Okay.
Yeah. All right. Or I guess you could also, right, technically have an element where you're literally just shearing it apart, and then, you know, that would be a little bit different. Yeah, there would still technically be the same, there would be bending and stuff, but that's more of a Timoshenko, just pure shear situation, so that would be different. All right, so next page, let's consider some flanged beam, and at the bottom we've got a box beam that we'll look at. So here I'm going to outline some axes. So first of all, noting the neutral axis there. This is a noisier location, I guess, this room. It's nice to have the windows open though for ventilation. All right, so we got the neutral axis at the centroid. We proved that last time, right? And we will align our other axes up here. So we got X along the length, Y, and then Z, like that. All right, so in this cross section, we have a width of the flange, all right, call that BF, and a width of the web, which we'll call BW. So since the width changes along the depth of the cross section, we have to think about different points within that cross section for calculating shear stress and developing the shear stress profile. So we'll consider a point here. This is the bottom corner of the top flange. We'll call that point A. And we'll consider a point that's somewhere in the web. All right, we'll call that point B. So within the flange, the B term would be BF, and the Q for point A specifically, all right, we would use the area above that point to the extreme fiber. So since I chose the bottom of the flange, it's going to be the entire area of the flange. And then we have to multiply that area times the Y bar for that area, which is going to be measured from the neutral axis to the centroid. And I'm actually going to show that on the image below. So this will be your cross section in the YZ plane. Here's the neutral axis, and then this distance right here is, we'll call that YF bar. So that's what we're going to use to calculate QA. For the web, all right, B would be equal to BW, and Q for point B, we would, all right, consider where this point is located and then all of the area above that point. So we would need to add to our QA the area within the web that's above B. So we can say it's going to be equal to QA plus A2 Y2 bar, where Y2 bar is the distance to a point at the centroid of that second area. So I'm going to label this as point B. Okay, so yeah, sorry. I misread my own notes. So the neutral axis is way down here. My apologies for any confusion there. So YF bar is measured from the neutral axis to there. Y2 is measured from the neutral axis to this point. All right. So then you can calculate the shear stress at A as V times QA over BF and IZ. And the shear stress at B is V times QB over BW and IZ. So then if we wanted to draw the shear stress profile, those are the 2 points that we would need to, I take that back. There's another point we would need to calculate, right? So we considered point A, which was within the flange, right, at the bottom of the flange, but the shear stress is going to change significantly as soon as we enter into the web, right? So if you consider a point that's at the top of the web, it's going to have the same Q, right, as point A, but it's going to have a different width, right? So the shear stress is going to jump significantly in magnitude with a smaller width at the web. So we can expect that profile if we're now looking in the XY plane. All right, so here's your neutral axis. That shear stress profile, we know it's going to be 0 at the extreme fibers, and then it's going to be some value at A. It will vary parabolically between those points. And then there's going to be that jump from BF to BW. Oh, that's not what I meant to do. All right, to something here. And then you're going to have parabolic variation along the web like so, and then it will be symmetric on the other side. So this sketch represents magnitude of the shear stress. The direction we typically note just with arrows in the profile like that. And the direction is going to be consistent with the direction of the shear on the cut face. So I might go back a couple pages to note that, because I don't think I wrote that down. Yeah, question?
Is Y bar F including the area of the web for like where it's coming
The
from?
distance, yeah. So the total distance for Y bar F is from the neutral axis to this point.
But
Yeah.
does it go into the centroid of just the top?
Yep. Yeah. So it's
not including the area of the web in that?
correct.
centroid?
Yeah, that's correct. Yeah. So I misunderstood at first.
Yeah.
Yeah, so Y bar F is the distance to the centroid of the area above point A. Yeah.
Oh, it's at the bottom corner, right?
Yeah. Yeah.
But
So,
Y bar 2 would include the area of the flange.
correct. Yeah, so, well, no, sorry. Y bar 2 doesn't, all right. The Q for B does include this, right? But because it's two different shapes, we want to break it up, right?
Right.
So you could, like if you wanted to, you could calculate the centroid of this whole thing, and you could say, all right, the area of this times the centroid of this. But it's, yeah, but it's easier to just do QA plus Q2 to get QB, right? Yeah. Yep, good. All right, so now if we consider, all right, a tube section, just for something a little bit different to look at. Here, let's think about this as the neutral axis. So this would be a rectangular tube. We're only looking at the top half. We consider this to be one dimension, we'll call it D. All right, and we consider that depth, or half the depth, to be C. And then if each wall has a thickness T, then we could predict that the maximum stress would be at the neutral axis. Right, and at that location, the width that we would use in our stress calculation would be equal to 2T. So I just like to point that out because you want to make sure that you use the total width of the material at the location where you're calculating shear stress. All right, so if you draw a line through the cross section at that point, however much width of material you have there, that's what you use for B. And if it's thin-walled, I'll make that more clear that it's a T. All right, if it's thin-walled, then the other dimensions are going to be much larger than the thickness. So the Q calculation at the neutral axis would be, right, if we think about it as breaking it up into rectangular sections, right, something like this. It would be D times T times C. All right, so that essentially would be your A1 times Y1 bar, represented by the yellow highlighted area. Oops.
Is that D times D or
Yep. No, yeah, good question. That is D, the dimension D times T. Yeah, fair question. Can clarify that. There we go. And then we would want to add to that evaluation for Q of the two vertical sides. So that would be C times T times C over 2. And then there's 2 of them, so we would just double that value. All right, so this would be A2 and Y2 bar, where A2 is the orange area. And then the maximum shear stress at that neutral axis would be VQ over 2T IZ.
So it seems like for the most part, our flanges on any of these shapes really contribute almost nothing to our shear capacity then.
That's correct, yeah. Yeah, the shear is mainly carried by the web. Yeah. So,
makes sense?
yeah. Yeah, so if you need to increase the shear capacity of your beam, for example, the most efficient way to do it is to choose a slightly deeper beam. Yeah, you wouldn't want to mess with the flange widths necessarily. That would be more relevant for bending, yeah, moment specifically. All right, so now we're going to roll into an example that's going to be kind of a comprehensive beam analysis. So we're going to do all the things, finding normal and shear stresses and profiles for those stresses, finding the principal stresses and maximum shear stress at the top of the web, and then finding the beam deflection equation. So all of it rolled into one. We'll see if we get through it today or not. If we have to finish it up on Monday, that's no big deal. All right, so pretty simple configuration here, a cantilever beam with a uniform load. Reactions are shown, and the cross section is a T shape, right? So we'd like to draw the shear and moment diagrams. So our shear is going to start off with positive 20, and then because it's a uniform load, it's going to decrease uniformly to 0 at the free end. So from the shear diagram, we can quickly discern that our maximum shear is going to be 20 kips at x equals 0. And just as a reminder, right, your shear sign convention is going to be positive downward on the right side of a segment and upward on the left side of a segment. So that'll come into play later when we get into drawing the stress profiles and interpreting direction of shear for principal stress calculations, or Moore's circle if you do that, whatnot. All right, moment diagram then would start off with a negative 100 kip feet from the reaction moment, and it would increase quadratically to 0 at the free end. Something like that. Oh, where'd it go? There we go. All right. So, moment diagram is useful for identifying the maximum moment. Of course, this is a very simple example, but if you have more load at play, definitely want to draw shear and moment diagrams to confirm those values. And then for positive moment, all right, our sign convention is as shown below. The configuration that would cause the beam segment to smile. All right, so now diving into the cross-section, we just need to obtain the geometric properties here for stress calculations, etc. So again, we're dealing with our YZ plane. Neutral axis is shown, but we need to find the distance to it, right, the Y bar. So we can note that the area is going to be 12 from the top flange plus 16 from the web. 28 square inches for the whole cross section. And then Y bar, we use our formula, all right, summing the products of the areas and the distance to the centroids divided by the total area. So that distance for the top is 9 and for the web is 4, divided by 28 gives us 6.14 inches to the centroid. And then our moment of inertia I'm gonna say, let's see, I'm just gonna say I, since we're only dealing with one axis of bending, just say I is equal to IZ, and then we can drop the Z from now on. And our formula is the summation of BH cubed over 12 plus AD squared, right? Remember parallel axis theorem there. So that's going to be 2 times 8 cubed over 12, starting with the web, plus 16 is the area of the web times the distance, D, remember, is the distance from the centroid of the whole section to the centroid of the piece that you are calculating in that moment. So, and it doesn't matter what order you take that difference because that term is squared. And then we have 6 times 2 cubed for the top over 12 plus 12 times the difference between 9 and 6.14 squared. So that comes out to 261 cubic inches. Just a little recap there on calculating moment of inertia. I knew you all probably didn't need it, but sometimes it's helpful. All right, so I'm going to note on this cross-section the points that we're going to be considering throughout this solution. So we'll call the top of the flange corner A, the bottom of the flange B plus, and then the inside corner will represent the top of the web. We'll call that B minus. We want to use the B in both places just as a reminder that at that location, we're going to have the same Q, but a different width, right? So different shear stress. And then C at the centroid and D down below. All right, so we can start with stresses at x equals 0. Why x equals 0? Because that is the location where we have maximum shear and maximum moment. All right, so first at point A, since it's an extreme fiber, we know the shear stress is going to be 0. All right, so that one's easy. The normal stress in the x direction at A will be negative m times y over I. So that's negative m is negative 100. So we have a double negative here. And that's in kip feet. So we want to convert to inches. All right, and then y is going to be the distance from the neutral axis to the point where we're calculating normal stress. So that's going to be the total depth of 10 minus 6.14. And then in the denominator, we have our 261 cubic inches. Or, sorry, inches to the fourth. Why did nobody correct me on that? Did you not catch that? All right, inches to the fourth for moment of inertia, right? All right. So this comes out to be 17.75 KSI. And it's going to be in tension since we got a positive result. All right, so as a gut check, that makes sense, right? Cantilever beam with a uniform load on it is going to deflect like this, where the top fibers will be stretching and the bottom fibers will be compressing. So at the top, we expect to see tension. So then at B plus, which is the bottom of the flange, we can no longer say our shear stress is 0, so we have to calculate it. VQ over BI. So that's going to be 20 kips is our shear at x equals 0, and then Q is going to be the area above B plus, so that's just going to be 2 times 6. All right, inches squared for the area, and then multiply that by the distance from the neutral axis to the centroid of that area, which will be 9 minus 6.14, right? So taking total depth is 10, so this point is 9 from the bottom, and then this is 6.14. Yeah, that's correct. Okay. 9 minus 6.14. Whoa, did not mean to erase. There we go. All right, so that's A1, and that's Y1 bar. So that takes care of the numerator. In the denominator, we have the width of the flange, which is 6 inches. And our 261 inches to the 4th. This comes out to 0.44 KSI. And then the normal stress at this location, right, of course using the same formula, negative my over I. M is the same as before, I is the same as before. The only thing that changes is that variable distance y. So with y now being equal to 8 minus 6.14 for point B, we get normal stress at B plus is equal to 8.55 KSI, also in tension. All right, so for B minus then, which is the top of the web, we got shear stress, again, VQ over BI. So we can just take, since everything V and Q are the same and I is the same, the only thing that's different is the B in the denominator. We can just take the value from B plus, 0.44, and multiply it by the ratio of those denominators. All right, so we're going from 6 inches to 2 inches. And that gives us 1.32 KSI. And then our normal stress at that location will be the same exact thing that we calculated in the previous step, because that is not dependent on width. So then we have the neutral axis now, where normal stress will be 0, so all we need to do is calculate the shear stress. So we're going to have a new Q to calculate, all right? So 20 kips times, we want the area below point C, all right? So this is a trick, right? If you have a section like this where you have a more complicated area above it, use the area below it. It'll be a lot easier, right? So we can choose either direction since we're at the neutral axis. All right, so we want to use the area below C. So that's going to be 2 inches times 6.14. And then the distance, that y bar will be just that, it's still the same definition, right? The distance from C to the centroid of the area below. So that's going to be 6.14 over 2. And I'll note what these are. So that's the area below C. And this will be the y bar for that area. All right, so in a sketch, we're using that area and that distance. All right, then in the denominator, we have the web width of 2 inches and moment of inertia. So we get 1.44 KSI. And as noted earlier, sigma is equal to 0 since y is equal to 0 in that formula. Right. All right, and then finally at D, it's an extreme edge, so shear stress is 0. Normal stress at D, using the same formula as above, you would get 56.5 KSI in compression. All right, and that would be plugging in y of negative 6.14. To end up with a negative result. All right. So yeah, we made it about halfway through that example. We'll finish it up on Monday with drawing the shear stress distribution, normal stress distribution, and then calculating the principal stresses. All right. Questions?